So, my dear students, we will discuss today the governing equations of fluid mechanics. So, in the 8th class of our transport phenomena, we will discuss the governing equations of fluid mechanics. Governing equations of fluid mechanics. In this class, we will try to understand that what are the basic governing equations of fluid mechanics and what is the basic philosophy behind all these governing equations of fluid mechanics. So, basically, the basic equations which govern the entire fluid mechanics section of your transport phenomena syllabus, that is called the momentum transfer. So, basic equations are governing equations are number 1 is the equation of continuity. Second is the equation of motion, and third is the equation of energy. If you closely visualize such equations of the fluid mechanics, you will find that number A, such equations are regarded as cornerstones of computational fluid dynamics, are regarded as cornerstones of computational fluid dynamics, abbreviated as CFD. People who wish to do their BTech or MTech or IDD project in the field of the thermodynamics of phase diagram utilizing the Calfed software, you will find such fundamental concepts are of enormous importance at those places. So, such equations are regarded as the cornerstones of the computational fluid dynamics, CFD. Number B, such equations speak physics. That means, in all these three equations, the fundamental concepts of physics are being utilized in order to arrive at such equations. And number C, these equations are based on the fundamental principles such as principle of conservation of mass, principle of conservation of momentum, and principle of conservation of energy are also called as the first law of thermodynamics. So, equation of continuity is based on that is a derivation of the principle of conservation of mass, whereas this equation of motion is basically based on the principle of conservation of momentum, or in other words, this is also a consequence of Newton's second law of motion, that is the rate Newton's second law of motion, that is the rate of change of momentum is equal to the force applied on a particular system under consideration. So, this is called also the Newton's law of motion. Third one, that is the equation of energy is based on the principle of conservation of energy, or in other words, it is also a consequence of the first law of thermodynamics. So, the modeling of any fluid flow, we can do by utilizing such steps that I would like to mention here. So, hence modeling of fluid flow can be executed through the following steps. The steps are: number 1, choice of fundamental principle of physics, of physical principles. This is the first step. In order to model the fluid flow, that you have to select the first fundamental principle which may be of the importance in order to derive that particular governing equation appropriate for the modeling of the fluid flow. So, the choice of the appropriate fundamental principle of physics. Number 2, appropriate physical principle as discussed above, or better to say as decided above. Is applied to a suitable fluid volume called as control volume. Now, doing in this manner, equations embodying such fundamental principles are arrived. Now, in this manner, the equation which have been arrived on the basis of all these 3 aforesaid steps are capable enough to model a fluid flow. So, these are the steps which needs to be applied in every equation which stands for modeling of fluid flow. Now, the question arises how the selection of this control volume can determine the nature of the equation that we are getting. Let us suppose if I am considering control volume as a rectangular parallelepiped during the flow of a fluid having quarter minus edge length of the infinitesimal length infinitesimal magnitude along x, y and z axes, then such type of equation are called as differential balance equation. If I am taking the example of the principle of conservation of mass and I am taking a rectangular parallelepiped of the quarter minus edge length dx, dy, dz along these three mutually perpendicular Cartesian axes x, y, z, then the equation embodying such fundamental principle that we are getting are what are known as differential balance equation. On the contrary, instead of taking a difference the infinitesimal edge length rectangular parallelepiped or rectangular cuboid in any fluid flow, if I am taking the inlet and outlet of a system or entry and exit of a system as 2 points in the fluid flow, then in that case the mass balance is obtained, momentum balance is obtained, energy balance can be obtained, but those equations are called, instead of differential mass momentum energy balance, they are called overall mass balance or overall energy balance or overall momentum balance. While discussing these type of the differential balances, an important thing which encounters at many places in the classes to come is called the substantial derivative. So, prior to dealing with all these type of differential balances, it is customary to have an idea about the substantial derivative. The question arises what the substantial derivative is. So, let us try to develop the concept of substantial derivative or material derivative and its utility in continuum fluid mechanics or momentum transfer. In order to have an idea for such things, substantial derivative, first the matter of topic is substantial derivative. This substantial derivative it is an important derivative, in the field of aerodynamics. How it is important to aerodynamics, I will come later on once I will establish the concept of the substantial derivative. Now, let us consider an infinitesimally small volume element in the flow through Cartesian spaces as shown below. Let us assume this is a Cartesian space, these are the x, y and z axes. Let us suppose this is the differential, this is a number 1. This is the infinitesimal volume element of fluid at time t is equal to t1. let us suppose this is the position number 1, another position during the flow, let us suppose this is another position of flow of this infinitesimal volume element. This is the position 2 at time t equal to t2, and let us suppose this is the flow direction. So, let it be vector v1, and at this point let us suppose the velocity is v2 vector. Okay. This is the diagram that this is showing a Cartesian space. Now let I, j, k, these are the unit vectors along x, y, z axes. Okay. And let us suppose u, v and w are the components of vector v along x, y, z axes. Then definitely we can write here the vector v, that is equal to u I plus a small v j plus w k. Here I would like to emphasize one point, that generally, except for this diagram in this class, here I am using this v symbol, the capital V with the vector sign for the velocity. Instead, at the other places, if only the capital V letter is being utilized, it means you should understand as its volume rather than velocity. So, velocity vector is equal to u I plus v j plus w k, where u is a function of x, y, z and time coordinate t, v is a function of x, y, z, t, and similarly w is a function of x, y, z and t. Now, considering an unsteady flow, considering an unsteady flow, u, v, w all are the functions of space and time. In addition, there will be one associated scalar field What scalar field can be assumed with this flow? That is that is the density, because of the fact that on mathematical ground the density is a scalar field. So, the density at the point number 1 and the density at the point number 2 during the flow of the fluid may be assumed to have some different value, because the flow is unsteady in nature. So, the density may change. So, scalar field, there will be one associated scalar field called density. defined as, now it requires a definition of this density scalar field. So, in the context of an unsteady state flow, defined as rho, and that rho is a function of x, y, z and t, and also corresponding to V1 vector and V2 vector. Corresponding to V1 vector, let it be the density, the rho 1, that is a function of corresponding to this V1 rho 1, that is the density at point number 1, that is a function of x, y, z and t, and V2 vector corresponds to a density field rho 2, that is a function of x, y, z and t. Now, expanding the function rho is equal to rho x, y, z, t in form of a Taylor series. Expanding rho is equal to rho x, y, z, t as Taylor series, we can write the rho 2 is equal to rho 1 plus d bar rho by d by x at the point 1 into x2 minus x1 plus d bar rho by d by x, sorry, d bar rho by d by y 1 y2 minus y1 plus d bar rho by d by z at the point number 1 z2 minus z1 plus d bar rho by d by t1 t2 minus t1 plus higher order terms. That means the higher order in terms of the differential coefficient, that is the first derivative, second derivative, so and so forth. Or we can write rho 2 minus rho 1 divided the whole expression by t2 minus t1, that will be equal to d bar rho by d by x 1 x2 minus x1 divided by t2 minus t1 plus d bar rho by d by t 1. Let it be question number 1. Let it be question number 1. Now, keep this equation and other things can be removed for the time being here. So, the left hand side of the equation number 1, left hand side of equation number 1 is equivalent to average time rate of change of density, fluid element as it moves from point number 1 to point 2, from point 1 to point 2, or moves through point 1, what does it mean? Point 1 is not an arbitrary point. That means the point at which you have to make the study. That means if you are studying the flow of air, in order to have meteorological information about the weather at the particular position 1, it means you have to keep in mind the rate of change of the density of the air at a particular point number 1, that is a particular place, let us say as the Varanasi BHU. So, this basically is giving the average time rate of change of density as the fluid volume moves to the point number 1. Basically, this is called the substantial derivative. This is called substantial derivative. This is called substantial derivative. This is called the substantial derivative, and here observer's eye, and here observer's eyes are fixed with the moving element, and watches the density change while moving through point number 1, point 1. Okay. On a contrary, this value, that is the delta rho by delta t at 1 is a quantity which describes the rate of change of density, of fluid at point 1, rate of change of density of fluid element at point 1. This is a basic difference between the normal derivative and the substantial derivative. Now you can remove this. Now we can see now limit T2 tends to T1, x2 minus x1 divided by T2 minus T1. Basically, it should be equal to how much? It should be equal to the component of velocity along the x-axis, that is equal to u. Similarly, limit T2 tends to T1, y2 minus y1 divided by T2 minus T1, that should represent the v, and limit T2 tends to T1, z2 minus z1 divided by T2 minus T1, that should be equal to w. So, taking limit in the equation number 1, taking limit in the equation number 1, we can write this substantial derivative, it is represented by a letter capital d rho upon dt. Try to remember. We can write this substantial derivative d rho by dt, that should be equal to u d by rho by d by x plus v d by rho by d by y plus w d by rho by d by z plus d by rho by d by t. That will be question number 2. So, defining now the two different operators. Now, defining the operators. Now, defining the operators as d by dt, that is a substantial operator, that will be equal to d by d by t plus u d by d by x plus v d by d by y plus w d by d by z. So, this is called your substantial derivative operator. And another operator is the del operator. This is defined as I d by d by x plus j d by d by y plus k d by d by z. So, the equation number 2 can be transformed as d by dt in terms of operator d by dt, that is equal to v vector, you can easily see v vector dot delta dot v, no, v vector dot delta plus d by d by t. This is the form of the equation number 2 in terms of the operators only. Here, this quantity, the d by t, is called the total derivative. It is called the total derivative, and this quantity v vector dot delta, this is called the convective derivative. So, these are the parameters, these are the terms which often will be encountered derivative, that will often encounter in the case of the other equation that we are going to deal in the next class, that is the differential mass balance and the momentum balances. Thank you.